very heterogeneous. And even if the people talk about what is called a narrowly distributed or a monodispersed homopolymer, it still contains a large number of different chain molecules. For example, if you have a typical sample which you can prepare by anionic polymerization having a degree of polymerization of hundreds or so and a very narrow polydispersity like 1.05, then within the limits where you have 95% of all the chains covered, you still have 88 different species, all differing in their degree of polymerization. If we go to an even higher degree of polymerization, here is shown on the degree of polymerization, average degree of polymerization of 1,000, again very narrow distributed, you already have nearly 1,000 different species, 1,000 different molecular weights, so 1,000 different species that you have to consider about. Well, that is if you have a simple, quite simple homopolymer. What happens if you have a copolymer? Well, let us assume that you have a copolymer, a binary copolymer, having a degree of polymerization. Then you can have either 100 monomers of type A and 0 of type B. You can have 99 of type A, 1 of type B, and so forth. So in total, you have again, if you have a single degree of polymerization of 100, you have 100 different species. Again, if you take into account the different arrangements of the monomers in the chain, the number increases even more. So again, it's a huge number of different chains that you have to consider. That means we have a large number of different chains in the polymer sample, and if we have a copolymer, we have a large number of different compositions for each degree of polymerization, and I claim large times large is a huge number of structures that we have. And if we consider the arrangement of the monomer units along the chains, so what is called the microstructure, then we have a huge number times something large. So it's a giant number of different structures that we have to deal with. And if we would like to characterize our materials, then we have to find out which structures do we have. But of course, it's a giant number of structures, a giant number of peaks that we like to generate is not possible in a single dimension at all. So one of the reasons why we would like to use two-dimensional chromatography, and that is also true if you have low molar masses and or even low molar mass normal substances, then we would simply increase the peak capacity. So the peak capacity is nothing else than the number of peaks that we can resolve in a reasonable time. And if we do it in linear fashion, then we have a peak capacity n1. And the good thing about we can increase the peak capacity if we go to longer and longer times, to longer and longer columns. We can increase the peak capacity in one dimension. But if we use two different dimensions, then in the ideal case, the peak capacities of both dimensions multiply to each other, and that increases tremendously the number of peaks that we can separate. That is a more or less a formal argument to use two-dimensional chromatography. But first of all, we have to ask ourselves why we would like the separation. Well, if you have two samples which in their average composition, like here the number of red and blue spheres are identical, then we would assume that both samples are identical in terms of composition. If we count the number of chains in both of these samples, so if we measure the average molecular weight, the outcome would be, in both cases, we have 5 molecules, and if we divide our, 100 spheres by the number of 5, we have an average degree of polymerization of 20. In both of these samples, we have the same composition and we have the same average molar mass. However, if we look carefully, like we do here, if we separate our samples, then we see, well, obviously, both samples are completely different. You have in the one sample, you have quite homogeneous structures and all of identical structure here on the right-hand side. And on the left-hand side, you have a quite heterogeneous structure. You have backbone chains which are not grafted, and you have free grafts and so forth, and you have different grafting efficiency on the chains. So the average number, the average composition, and the average molar mass can be determined by standard methods like NMR and the molar mass by light scattering, osmometry, and so forth. But if we would like to have a deeper look, we have to separate the samples to find out all the tiny details in the samples. And you can ask, why should we use two-dimensional chromatography? Let us assume that we first do a separation like we did before. In the y-axis, we would do a separation, and we would see two peaks. Like in the upper right example, we do a separation into the direction of the y-axis, for example, in terms of chemical composition, and we see two peaks, and we are happy because, well, there are apparently two species in that. We do a GPC separation, which goes here to the right axis on the horizontal. Again, we see two peaks, and we're so happy because, well, apparently we have two chemically different species, and we have two species of different molecular weights. So apparently, well, we have two species, and one of the peaks in the HPLC belongs to a certain peak in the HPLC. But as you can see, you can have, in the lower part, you have again two peaks, but the order is reversed. Here you have the high molar mass, or the first peak in the HPLC direction in the vertical is now the one which is on the right, and the peak which comes out late in the HPLC, it's the upper one, comes out in the SEC first. So apparently by these two methods you cannot distinguish which peak belongs to which chemical composition, which molar mass is correlated with which composition. You can even not determine the number of different species that you have, because as you see on the two pictures on the right, both of these three peaks will have coallusion in the GPC direction in the upper panel here, and you might have also coallusion at the late allusion volume, and again you have in both directions two peaks, although you have three components, or you can have four peaks, and you have also two peaks, three components and two peaks in each direction. So the two-dimensional representations, either if you have a GPC representation or an HPLC representation, or both of them, will not give you the true information how heterogeneous and how complex your sample is. And that is why we would like to use two-dimensional chromatography. Well, what we can do is, in two-dimensional chromatography, we have this complex polymer sample, which is here on the left-hand side, and we can first do a separation, for example, according to size, which is here on the lower part of the slide. And as you can see, if we do a separation by size, you have, well, species of the same length, of the same number of spheres, but all of these fractions are heterogeneous, are still heterogeneous, because here you have a large number of blue spheres, and here you have a lower number of blue spheres, although they have both the same length, the same molar mass. The same is true here. You have completely red chains, you have completely blue chains, and so forth. So although you do a separation by size, you still have heterogeneity in terms of chemical composition. The other thing is, it's the same is true if you do a separation, an ideal separation based on composition. You might have a very nice separation by composition. You have the completely red chains here and the completely blue chains on top, and in between you have a separation by chemical composition. But all these chains, because you do a separation by composition, are of different molar mass. And only if you would take this fraction having a certain composition and inject it later on into the GPC, then these four species fall apart and give you the different peaks. So that is a way we would like to do the separation by two-dimensional chromatography. First do a separation by one parameter, and then re-inject each and every fraction into a second dimension, into a second separation step. Well, how can we separate? Well, we have different structures, we have different features of our polymer. One is simply composition. So as I have explained before, composition times size. Size means size exclusion chromatography. So we can separate in one direction by composition, the other one by size. We can have different functionalities. For example, if you have a polystyrene or a linear polymer, and you have OH groups at the end because you would like to use these materials later on to cross-link or to chain extend, then you have to make sure that really all of your species have two functional groups. And if you separate by functionality, then you lose the information about the size. So in the second dimension, we can do a size separation analysis by size exclusion chromatography. you can have something else, molar mass times size. Well, if you do a separation by molar mass, then, for example, a branched and a linear polymer might have, although they have the same molar mass, will have different hydrodynamic volumes. So there might be an option to separate, if you use in one dimension a separation method which is based on molar mass, and the second dimension by size, you might be able, for example, to separate branched polymers. You can have, you would like to use block lengths of one block. Assume that you have an AB block copolymer and you would like to do a separation of block size A, and in the second dimension you would have a separation by the complete molar mass. Then you have a very nice information about how is the complete block length depending on the block length of type A. Degree of branching times size, and all these kinds of things. And one thing which you can also do, but is size times size, meaning you have size exclusion chromatography in both dimensions, but that is actually useless because you get no additional information for that kind of a two-dimensional separation. So what we need apparently is different separation mechanisms. And the first separation mechanism you might think of if you talk about polymers is size exclusion chromatography. It is certainly the most frequently applied separation chromatographic separation type, and it simply separates according to the size. And if you look here, these structures, which are all of the same size, as indicated by these black lines, they have the same size, but certainly their molar masses are different, or their compositions are different, and so forth. So size exclusion chromatography alone cannot resolve the problem. If we would have to separate by other structural features, for example, by end groups, like here with we would like to separate the linear chains without this yellow end group, and with the yellow end group we need a different separation mechanism. If we would like to separate these structures by chemical composition, then we also have to use a different mechanism. So the ultimate requirement for successful two-dimensional liquid chromatography of polymers is that you have a non-size-based separation in one dimension, because in, I would say, 80%, 90% of all cases, one of the dimensions that you will use is size exclusion chromatography, and now you need another separation mechanism which responds to a different structural property and not only according to size. Well, question is how we can do that. What tools do we have to play around to get other separations as which are not based on size exclusion chromatography? And basically we have different options. You know, size exclusion chromatography is a method where you have in your column a sponge-like material, and your larger molecules have no way to penetrate all of the pores of the chromatographic column. So the larger polymer molecules elute early, and smaller ones, which can penetrate or partially penetrate the pores, will stay longer in the column and will elute later. And therefore you have in size exclusion chromatography, if you have no interaction between the stationary phase, no entalpic interaction between the stationary phase and the molecules, you have the high molar mass materials coming out early and the low molar mass coming out late. What happens if you allow for additional attractive interaction between the repeating units and the stationary phase? In that case, the number of attractive sites increases with molar mass. So the more repeating units you have in your polymer, the larger your molar mass, the stronger the polymer will be retained, and that happens very rapidly. You have such a kind of nearly exponential increase in retention time. And that is what we call liquid adsorption chromatography, isocratic liquid adsorption chromatography. And under these conditions, the molar mass increases, retention increases very, very strongly with molar mass. And in the end, even if you have a quite narrow distributed sample, some part of the material might stay simply on the column and will you will not see it within a reasonable time. Well, keep in mind, you don't have a single molar mass. You have always a molar mass distribution. So on the y-axis, you have a certain range. And if we have now different species, then you have co-elution of different molar masses, in size exclusion and in liquid adsorption mode. Let us assume you would like to do a separation according to functional groups in your polymer. How would you like to do that? If you use size exclusion chromatography, you will have most probably co-elution of the functionalized species with slightly different molar mass of the non-functionalized species, so you get no separation. The same is true in liquid adsorption chromatography, because you get a very broad peak due to the molar mass distribution. And if you have a tiny end group, which gives rise to additional adsorptive end groups, you will have again a co-elution of your functionalized polymer with the non-functionalized polymer of a slightly different molar mass. What happens now if we have two solvents, for example, as one solvent where our polymer sample will experience SEC conditions? So it's a very strong solvent, you have no attractive interaction with the stationary phase. In this case, our homopolymer would reveal such a size exclusion-like behavior. And now, add a little bit of your solvent, of a weak solvent, which allows for attractive interaction. Then you make your polymer less strong, and at a certain point, your polymer will experience adsorbing conditions. So if you turn basically your size exclusion calibration curve from this side over here. You can do it the other way around. You can say, well, I start in liquid adsorption chromatography and add a little bit of a stronger solvent, and finally you should end up with a size exclusion mode. And the very fancy thing is that if you do it in the right proportion, you end up with something we call liquid adsorption chromatography under critical conditions, and under these conditions you will not experience any molar mass effect on the elution of your polymer. And the good thing about it is, well, it takes some time to establish these conditions, but what you have now under these under these critical conditions, how we call it, we always claim, well, we make the repeating units chromatographically invisible. And if you now have a polymer chain which has end groups and repeating units, and you make the repeating units chromatographically invisible, meaning they don't contribute to the retention volume anymore, then basically your elution or your retention time is determined by the visible part of the polymer, which is now the end group. So at critical conditions we have an option to separate polymers according to the end group, for example, or in general do very tiny differences in structure. So these are three modes of chromatography we can use, although liquid adsorption chromatography due to the very, very strong adsorption and the very long retention times isn't that well suited. If you go to higher molar masses. And what you usually do if you would like to separate according to chemical composition, because in liquid adsorption chromatography you stay for infinite times on the column, we change the eluent strengths. So we start with a weak eluent strength where the polymer is adsorbed, and then we add a stronger eluent so that the polymer starts to desorb. And what you end up is basically such a molar mass dependence where you have at lower molar masses, you see some kind of molar mass effect still. There is some increase in retention volume with molar mass. And if we go to higher and higher molar masses, basically the effect of molar mass on retention vanishes. And that means that each polymer, each homopolymer, or even each copolymer, as statistical copolymers, will elute at a certain time. And that gives us the capability to separate polymers according to the chemical composition of the structures. As I said, I could talk about these different modes of chromatography for a long time and show you applications for it, but I have here simply a list what might be a useful way to go if you would like to do a separation by certain parameters. For example, if you would like to separate by molar mass or by molecular size in one dimension, then the appropriate method would be size exclusion chromatography, gel permeation chromatography, or you can use temperature gradient interaction chromatography, which is a kind of a gradient chromatography, which is very sensitive to small variations in molar mass. If you would like to separate according to the chemical composition, then if you have blends, if you have statistical copolymers, gradient chromatography might be the method of choice. In certain cases, critical chromatography might be helpful if you would like to have a separation according to one block, for example. size exclusion gradients, and so forth. These are special techniques you can also use to separate according to chemical composition. Another parameter you would like to separate is you might like to separate according to the number of, or to the type or the number of end groups. In that case, most probably critical chromatography might be the method of choice, because otherwise you might have co-elution of different functionalities and different molar masses. And finally, if you would like to separate block copolymers or segmented copolymers according to the individual block lengths, so in AB block copolymer, we would like to separate not to according to the total length of the block copolymer, but only to the length of the A block, then you should use something like critical chromatography. You can look these things up, but that would be the method of choice to go. So these are the toolbox, or basically a toolbox which we can use, these separation techniques, a toolbox to put together for the two-dimensional separation. Well, if we'd like to now to do two-dimensional separation, what is the setup? So basically we have two individual chromatographic setups. We have a pump and an injector for the first dimension, and we have a first column. In this first column we do our first separation, for example, according to the chemical structure of the polymer. If we have here a gradient, we run a gradient here, and we do a separation which separates our mixture according to the chemical composition, and then we run into this valve. And this valve is nothing else now, it acts as the auto sample into the second dimension column, where we have again a solvent and a pump, and we pump now into our fractions into another column, for example into the size exclusion chromatography column, where we do a separation by size exclusion chromatography, and at the and the detector we then get a chromatogram. So what we obtain is chromatograms, size exclusion chromatography chromatograms for each fraction that we have transferred from the first into the second dimension. So we have a series of GPC chromatograms which are linked via the injection time to the retention time in the first dimension, and if you plot it in the right way, you get these fancy pictures. Well, the heart of the whole system is here this transfer valve. What happens in there? That is shown here. We come out from the first dimension column, and our eluent or our effluent goes into this loop, and as you can see, you fill, coming from the first dimension column, you fill this loop number 1 until it is filled. While you fill this loop coming from the first dimension column, the second loop, which is here, will be, or you have a pump which goes through the, the pump goes through these dotted lines, and you have then, and then goes through the dotted lines in this valve and pushes the content of oh, you're wrong. And pushes the content of the red loop onto column number 2. Then later on, if you have filled loop number 1 and you have analyzed loop number 2, you switch over, and then the content of the loops that you have just filled, coming from the first dimension, is now injected onto the second dimension column, while you now fill loop number 1. I'm sorry for that, but there is a mistake on the slide with the loops. I have to correct that for the handouts later on. Okay, so that is it, what we have. Basically 2 loops. One is filled while the other is analyzed in the second dimension, and then the first loop is analyzed in the second dimension while the second loop is filled. And that goes back and forth, and so you have a large number of different fractions going into the second dimension, and this results in these different SEC chromatograms, in this number of second dimension chromatograms. That is how such a system would look like. You have here the first dimension setup, which consists of a pump. You have here the autosampler, which where you introduce your sample. Then you would have a column, of course, and there is this you can have in column often, and there you might have this the second dimension loop, the transfer valve, and you have here the second dimension pump, and in the second dimension, of course, you need a detector. You might also use a detector in the first dimension to see what's going on there. So, but that is the setup that you have to use, basically 1.5 HPLC instruments and the transfer valve. Well, if you have now all these two-dimensional chromatograms, the chromatograms in the second dimension, you would like to plot them, and you can have them plotted like these very nice three-dimensional plots, which, however, look nice, but actually the information content is not as high as it looks like. I like more these contour plots where you have in this along the y-axis the retention time in the first dimension. You have on the x-axis the retention time in the second dimension, and the colors indicate the concentrations that you have obtained on each of these on these spots. The contour plot, you can also plot these things as so-called isolines. Again, you have along the y-axis the retention time in the first dimension, along the x-axis retention time second dimension, and now the circles represent lines of identical concentration, and that is something you can read much better than these three-dimensional plots. So there are various options to plot these things. I told you that in our two-dimensional chromatography we have this loop filling procedure. We have to analyze one loop while the other one is filled, and vice versa. So that means during the period that we run our size exclusion chromatography, we would like to fill the first loop. And that means, because you know size exclusion chromatography typically requires 50 to 45 minutes approximately, and that means we have to use very low flow rates in the first dimension to fill the loops, and in the second dimension we have to be as fast as possible. So flow rate is certainly an issue. For comprehensive two-dimensional liquid chromatography, and what comprehensiveness means I will explain in a few minutes, comprehensive two-dimensional chromatography requires very slow first dimension flow rates because the time for filling the first loop has to match the second dimension analysis time. Meaning slow flow rates in the first dimension and high flow rates in the second dimension. And here you have two options. If you would like to have a fast size exclusion chromatography in the second dimension, you can either use very high flow rates, and then you use typically short and very fat columns. But that means you have to have detection devices which can withstand these high flow rates. We use in these cases usually evaporative light scattering detection. Another way to speed up the second dimension analysis time is to use small columns. However, if you use small columns, you have a small pore volume and a small separation space, then band broadening issues become more important, and you have to think about that. Separation order and solvent consumption. Well, usually, as I explained, we use interaction chromatography in the first dimension, so some kind of gradient chromatography, critical chromatography, liquid distortion chromatography in the first, and size exclusion chromatography in the second dimension. Why? Well, if you use a gradient in the first dimension, if you use gradient chromatography, you usually have to equilibrate your system, and that takes some time. If you have therefore the gradient in the first dimension and an isocratic separation method in the second, you don't have the you don't need to equilibrate in the second dimension. That means you can speed up your second dimension analysis, which was, as explained before, requirement for comprehensive two-dimensional chromatography. Also, sample capacity is usually higher in interaction chromatography. So while GPC is quite prone to overloading, column overloading, and you get shifts in retention time and so forth, these effects are not as dramatic if you use interaction chromatography. Usually we can use more material, we can inject more material in the first dimension. Furthermore, if you would come from the size exclusion chromatography, where you have typically strong solvents and you would like to inject into the second dimension where you have interaction chromatography, where you have to absorb your material on the stationary phase, you might run into problems because a strong solvent in which the polymer, your effluent, your sample is dissolved when you inject it into the second dimension might be so strong that it prevents absorption to the stationary phase in the second dimension. And that is the reason why also we would like to use size exclusion chromatography in the second dimension. Some words about solvent compatibility. Keep in mind, you transfer your solvent from, basically if you use comprehensive two-dimensional chromatography, basically all of your solvent from the first dimension goes into the second dimension. That means you inject in the solvent coming from the first dimension, but in the second dimension you have a different solvent. So both solvents should be miscible with each other, and that is something you have to make sure. And of course, because the second dimension solvent is injected into the first dimension solvent is injected into the second dimension, again, yes, it has to be compatible with the column material in the second dimension because of the solvent transfer. That you have also keep in mind. Detection. Detection is another issue. Because you have a two-fold dilution, you end up with very low, because you do a separation in the first dimension, and all these fractions will be separated once more in the second dimension. You end up with very low concentrations at the detector. And that is the reason why we typically overload the column in the first dimension. Again, some overloading might be allowed because afterwards you will not have the full potential, but you get additional information. And another point is solvent transfer. Useful detection, it is very difficult to use, for example, an RI detector in the second dimension. Although this is a typical detector that you use in size exclusion chromatography. And the reason is that when you inject the sample in your first dimension solvent, you have basically 99.9% of solvent that you transfer in the second dimension and 0.1% of sample. And what you end up with, basically, if you would like to use an RI detector in the second dimension, you see a huge signal from the solvent, from the transferred solvent, and it takes very long for the RI detector to reach the baseline, and you will not see only tiny signal from your sample. UV would be a very good option in the second dimension, but only if you have suitable chromophores in your samples. And what we usually very often apply is evaporative light scattering, an ELSD detector. Here you have to make sure, or have to think about that the response is not linear. The evaporative light scattering detector evaporates your solvent, and basically you have a very good, you can also use it in gradient chromatography, what you cannot do, for example, with RI detection. Okay, some words about terminology. Basically, two-dimensional chromatography can be performed offline and online. At present, I have only talked about online measurements, but there are certain issues which are useful if you use it offline. Two-dimensional chromatography can be orthogonal. What does it mean? I will tell you in a minute. And also, it can be comprehensive. What is the benefit of offline and online? Online is quite clear. If we use this automated system where you have an automated transfer of the effluent from the first into the second dimension, it's automated, you can run it unattended, you don't have to worry about mixing up samples, about confusing samples, so it is certainly less prone to errors. The cons, it requires additional equipment. You have this question with detection, you have only tiny concentrations, so you have to use suitable detection. The solvents of first and second dimension have to be compatible, and of course solvent of the first dimension has to be compatible with the second dimension column. If you do the whole stuff offline, meaning I use a fraction collector, for example, at the end of my first dimension chromatography, then it's quite simple and cheap. First, I collect my samples with a fraction collector, then I take my samples, put it into the rack of the autosampler, put in another column into my system, and run the samples. So it's certainly cheap and and simple. It has an advantage if I have problems in detection in the second dimension, then I could run not one sample, but I can repeat the runs and can collect from several runs the fractions, and by this procedure I can enhance my concentration and I have less detections, less problems with detection. I have also an option if I have solvents which are not compatible in the first dimension, first dimension solvents which are not compatible with the second dimension column. I have the option to evaporate the solvents and exchange the solvents and can work them with a new solvent. So cons, certainly if I have to collect fractions, evaporate solvents, give in new solvents, put it on the auto sample, is much more labor and time intense, and certainly I or you or everybody can do much more errors in that case. Orthogonality. What is orthogonality? Orthogonality means I have two completely independent retention mechanisms in both dimensions. For example, if I use critical chromatography, where I have no molar mass effect at all, and I do later on the size exclusion chromatography, I expect to have a nearly orthogonal separation because size exclusion is separating to molecular size. So, but I will not see any effect of the functional end group, while in critical chromatography I have no effect of end group, or I have no effect of molar mass, but I have the effect of end groups. So both separation mechanisms are independent of each other. Orthogonality depends on the sample, on the way you would like to do your separation, so it's not something fixed. However, even if you have non-orthogonal separation mechanisms, this is not a requirement. Even if you have non-orthogonal mechanisms, you get an increase in information content from a 2D LC analysis. Comprehensiveness. Comprehensiveness means I transfer from each fraction in the first dimension of each sample components, I transfer identical fractions into the second dimension. This is in contrast to the old-fashioned hard cutting, where you take only fractions of, as a peak maximum, for example, in the first dimension and inject it. So comprehensiveness means you have to transfer, identical aliquots of all sample components from the first into the second dimension. That is one thing. And you should maintain the resolution of the first dimension separation. So you should not simply collect all the fractions from the first dimension and inject it and have all again collected, have transferred identical aliquots, but you have lost your separation. Okay, plotting two-dimensional, the comprehensiveness can you identify, or whether you have lost separation resolution in doing the two-dimensional system, if you reconstruct the chromatograms from the first dimension from the two-dimensional data that you have. Suppose you have this two-dimensional representation, then you can of course sum up all the for one SEC for one second-dimensional chromatogram, you can sum up all the intensities, and that should give you the intensity at this point in the first dimension where you have injected. And if you do that for all the different slices, then you end up with the reconstruction of the first dimension chromatogram like it is shown here, and then you have an idea whether you have maintained the resolution from this first dimension. Okay, is two-dimensional chromatography useful for something, or does it only produce nice pictures? No, because in a polymer world we would like not only to get nice pictures where you have a lot of peaks, but we would also like to get quantitative information. And for example, you can circle or you can identify peaks in these plots, and then you can determine the volume or the peak volumes or the peak area, which gives you information about the amounts of the different materials that you have. So that is one information. In addition, if we talk about polymers, we would like to get molar masses typically. And if we do a separation, then first the separation in this direction might be according to chemical composition into the y direction, and you have two peaks, but these are chemically different species. So what we would like to have is a method that we can determine the molar masses. Here, from the first glimpse, we would say both have the identical molar masses because they elute at the same elution volume. But as you know, size exclusion separation is based on molecular size and not based on molecular mass. So we should apply for this peak a different calibration curve than for this peak. And that can be done. For example, if you do that in the correct way, then you have here the separation. For example, if this would be a polystyrene, we would like to have a polystyrene calibration for this peak, or you can have a PMMA calibration for this peak. So if you have blends, that is easy. Simply tell, well, this is PMMA and this is polystyrene, and evaluate your chromatograms with two different, the two regions with different calibration curves. What happens, however, if you have a continuous separation, for example, copolymers or something, which range from 100% polystyrene up to 100% of PMMA? In that case, I have this very nice or ugly peak, and now I would like to have a calibration curve at the beginning on polystyrene, and in the end it should be a calibration curve for the PMMA, and that is also possible because you can interpolate from 100% polystyrene calibration to 100% PMMA calibration, and for a copolymer this would give you something like this, where you have really for each slice a calibration curve, adjust the calibration which fits to the composition of the samples. Okay, that is all you can do, what you can do in principle with two-dimensional chromatography. I would like to give you now some examples on real-life applications that has been measured already. Here's an example of functionalized PMMAs, which is taken from the group of Peter Schoonmakers in Amsterdam. And what they did is they separated in the x-axis according to by LCCC, by critical chromatography, meaning they separated along the x-axis by the number of OH groups. So you have non-functionalized, which comes out first. Basically, peak number 1 and 2 are the peaks which have no OH groups. Peak 3 and 4 have one OH group each, and peak number 5 has two OH groups. And as you can see, I have two samples which have no OHs, 1 and 2, but these differ in the separation in the second dimension because they have different molar masses. Same is true for 3 and 4, and so this is a way to separate according to functionality in one axis and size exclusion chromatography in the other axis. That is also a fancy thing. This you can regard it as block copolymers or also as a separation according to functional end groups. These are fatty acid ethoxylates, which are initiated, so it's basically ethylene, polyethylene oxide, and initiated by alcohols of various lengths. As you can see, if in the first dimension there was, that is now the y-axis, there was a separation by critical chromatography, so the lengths of the ethylene oxide units do not play a role anymore, and you do a separation according to the length of the alkyl groups that you have used to initiate the chains. And then each of these fractions was injected into a liquid adsorption chromatography run, because we have here quite low molar masses. You can do that, and you see that it's basically all you have for each end group, for each alkyl end group, you have a series of peaks, basically horizontal, because we have critical chromatography, molar mass does not play an effect in the first dimension, and these are individual oligomers having exactly the C18 end group, or these are C12, these are oligomers carrying exactly the C12 end group. That can be done as well, and it's also taken from the work of Jacques Raust. This is the first two examples have shown you separation by functional groups and size exclusion or molar mass, basically. Here is a separation where you have a carboxyl methyl cellulose, and that was separated along the y-axis by gradient chromatography, and carboxyl methyl cellulose, it can be regarded as a copolymer which carries cellulose units and carboxyl methyl units. And we have here a separation according to the according to chemical composition, and then we have injected each of these fractions, which is heterogeneous according to the degree of substitution, into the second dimension, and that was a mixture composed of two samples having very similar DS, very similar degree of substitution, and these are two samples having very similar molar masses but differ in their degree of substitution. If you would have done a GPC, you might have seen this peak and this peak. If you would have done only HPLC, you would have seen this peak overlapping with it, and that would give you another one. So only the two-dimensional chromatogram gives you the complete information. Graft copolymers can also be separated. In that case, a work from Sebastian Roos and Axel Müller's group. We have a separation by critical chromatography along the y-axis, critical chromatography for the side chains which have been n-butyl acrylate, and you see the residual side chains, the non-grafted side chains form a spot here. And if you now add the PMMA elutes earlier than the PNBA, you get this very nice separation, and you can have a separation into the individual side chains, residual backbone, individual side chains, and here in this direction you have the samples differing in their number of grafts. A separation by topology is possible, I told you that. If you run gradient chromatography on a branched and a linear material, you will recognize that you basically separate or strongly separate by molar mass. So if I do a separation in a gradient, I have the branched species and a linear species of identical molar mass at each elution volume, and if I inject this now into the size exclusion chromatography, the peak, also two different species will be separated because the branched molecule and the linear polymer of identical molar mass have different hydrodynamic volumes, so the branched polymer will elute later, and that gives the capability to separate branched and linear polymers. And here is a similar application on polystyrene stars. Again, gradient chromatography in this dimension gives you separation according to the molar mass. And if you have a mixture, then if you inject this into the size exclusion at this fraction, then the linear polymer at the identical molar mass has a larger size and will elute earlier in the size exclusion chromatography than the branched polymer. So these are applications, some of the applications that have been shown from various areas and different ways to separate. And with this, I would like to come to an end. I hope I could convince you, well, that polymers exhibit different types of heterogeneity, and that two-dimensional liquid chromatography allows separating very complex mixtures. You have to have the right combination of separation condition, and you can use online and offline. Both have their benefits. And you have to make sure that you have to optimize your parameters, but there is certainly help available. At PSS we have some experience with these questions, and if you have questions you can ask us. With this, I would like to thank you very much. I'd like to thank Derek Lohmann at the other end in the United States who organized this meeting, and I hope you could get some information, and if you have questions just let me know. Thank you very much.
Thank you, Wolfgang, for this interesting and I'd say rather deep presentation on 2D polymer analysis. I still owe you, before we head off to the questions, I still owe you the email addresses, which I now displayed in the chat window. If you want a copy of this presentation or the recording, as I said, just, and now I see the emails there, so sorry, Wolfgang. They were so light in the background that I didn't even see them. So you're more than happy to send us an email to request a link to the recording and to the webinar itself. As Wolfgang mentioned, we also have a little primer on two-dimensional chromatography of macromolecules that we have just basically reissued in the second edition, which you're also more than happy to request. We do have some questions. You talked about the 2D chromatography, outlined the different liquid chromatography techniques, but what you spared out basically is how are we going to control that, and how are we going to acquire data?
Well, oops. Yeah, basically we have our own software at PSS. We have our software package which can do that. Where you have basically you put in the number of fractions you would like to have. You have to add the flow rates in the second dimension and the first dimension, and then basically the program calculates when the loops are filled and so forth. I don't not went into the details because that was on the method and not on the software. To our knowledge, other manufacturers have also 2D programs, but I guess what I know is we are the only one that can evaluate later on molar masses and so forth. Is that the answers that you'd like to have?
Yep, that's at least something to kind of get us going. Then another question is, how does the polymer architecture affect the elution profile in 2D?
Yeah, basically, as I have shown in the last two slides, you can have different architectures eluting at different positions. Actually, the separation according to topology is still a hot topic. If you have heavily branched species like stars, quite dense species, then as I have shown, you can separate hyperbranched polymers from linear ones. Stars from linear ones. If you have just a single side chain somewhere, then to my knowledge there are not too many methods available. There is one method which is called molecular topology fractionation, which was invented by Dow and furthermore investigated in the group of Peter Schoenmakers, where you do separations in very, very narrow channels. And so a branched polymer needs to be more stretched than a linear one. And that means if you would like to press them through a narrow channel, you get different retention times. Unfortunately, this method is at present, and to my knowledge, can only be applied to polymers with very, very high molar masses, above 1 million or so, because the channels that we presently can reach are too large for lower molar masses. But so you have to distinguish between, if we talk about branching or topology, between heavily branched, then it works with a typical adsorption times size exclusion way, or might work with typical adsorption in one dimension, gradient adsorption chromatography, and you have size exclusion in the second dimension. If you have long chain branch polymers, that's what the polyolefin guys would like to have, then you still have problems because you don't have yet the efficient methods to get sufficient differentiation between a lightly branch molecule and a linear one.
And to just basically tie into that, if you then take it a step further from linear to branched on to cyclic polymers, what would you say is the best way to characterize cyclic polymers?
For cyclic polymers, it has been shown that cycles have elute late. If you use, for example, polystyrenes, and you adjust critical conditions for polystyrene, then it has been shown that the cyclic polystyrene elutes later on the critical conditions of under the critical conditions of the linear one. So there, probably the best method would be if you have broadly distributed cycles with broadly distributed molar masses, you should use most probably critical conditions in the first and size exclusion chromatography in the second dimension.
Thank you. I think more or less one last question, if there isn't any more. How do we ensure that actually all components of the sample have already passed the first dimension completely before we end the experiment?
Yeah, but of course you run your first dimension. Yeah, first you have first you have to set up your first dimension experiment, and you basically then you slow it down, and you know the length, the time that it requires, as in the same way as you know it from the one-dimensional experiment. So basically, you control first. You set up your first dimension method, and you control it in there. What you can do is, for example, you have to determine the recovery after your experiment. And then you assume that in the second, that the recovery will not change simply by changing the flow rates, because that's all you do in the first dimension. If you use your first dimension in the 2D plot or in the 2D experiment.
Thank you. And I guess we can squeeze this one in. Is it possible to distinguish between the group functionality, like that's probably, is that a W1 and W2 hydroxy from non-functional moieties in a polymer?
What was it?
So make that probably an, I can't get the Greek letters right. It's W1 and W2, so it's omega, yeah.
So it's, for example, a non-functionalized hydroxyl,
yes, from an omega-1 and an omega-2, yeah.
From B-functionalized. Actually, I have such a problem on my desk at present. The typical way to address this problem would be in the first dimensional liquid chromatography under critical conditions. Because critical chromatography means I make my repeating units invisible, and you should set up the system such that your repeating units become critical, and your end group functions should have a stronger retention, so that you bring additional retention into the system. So if you have OH groups on polystyrene, for example, then a silica column will probably do the job. You adjust critical conditions for polystyrene using, I don't know, the weak solvent chloroform or something like that, in a mixture with GHF maybe, and on a silica column, because then the OH groups certainly of your end groups will have certainly a stronger retention with a stationary phase than the repeating units. So the answer would be critical chromatography, and such that the OH groups or the functional groups have a stronger retention than the polymer. So that defines whether you should use a normal phase or a reversed phase column.
Thank you, Wolfgang. I think this more or less concludes our presentation on 2D polymer analysis. Again, thank you, Wolfgang, very much for your very interesting presentation. If there are still questions that are left unanswered, rest assured that we will answer them via email. Also, I have already seen a few requests for the presentation, and we will make that available to you later on. So then again, I'd like to thank everybody for joining the webinar, and Wolfgang for presenting it. And from Amherst, Massachusetts, it's basically good day, good night, or good morning, wherever in the world you are.
Okay, thank you very much everybody for joining us, and have a nice evening or a good working day. Bye.